Okay, yeah, so I like to thank the organizer for this wonderful opportunity to speak here. I'm going to talk about some of our recent work in thinking about what we call a synthetic gauge field for light. So this is in the general area of electromagnetism, which is really a fundamental interaction in nature. And the basic subject of electromagnetism concerns the interaction of charged particles, such as electrons, with the electromagnetic field, and the carrier of that electromagnetic field is photons, or the particle of light. So the fundamental particle associated with electromagnetism are the electrons and light. And the interaction between them produces wonderful physics as well as very important technological advancement. Here is a very nice example, I think Professor Noda also alluded to, of a light-emitting diode. This is a case where you send in an electron and the light come out. So that's revolutionizing lighting right now, and is a wonderful example of these two fundamental particles interacting together. And this has been recognized by a Nobel Prize in Physics to 3 Japanese scientists in 2014. So the subject matter of electromagnetism really underlies modern technology. Here's another example. When we think about computing, we are actually manipulate electron in our computer. And when we think about communication, for example, the global information infrastructure, the internet, actually we're communicating through light. So the capability of controlling both electrons and controlling light really underlies the information technology. And you heard a fascinating discussion yesterday about some of the implication of these technology in the artistic world. So this is a physics talk, so I would like to briefly review on the physics mechanism that we have in controlling electron and in controlling light. So as you learn in freshman physics, when you control electron, you basically apply a field. For example, if you can apply electric field, and in doing so, you would generate a Coulomb force that counters to the direction of the field. Somewhat more subtly, and this is something that will be the centerpiece of my talk here, you can also think about using what's called a magnetic field. And in this case, what you imagine is that you have a moving electron, and in the presence of a magnetic field, in this case, a magnetic field that's pointing out of the plane. And in doing so, you generate a Lorentz force. And this is a force that's perpendicular to the direction of the motion, as well as perpendicular to the direction of the magnetic field. Now, for our purpose here, it is actually very interesting to note that there's something special about magnetic field. It breaks what's called the time reversal symmetry. Since this is probably not an everyday concept, I want to illustrate the concept of time reversal symmetry with an everyday example. Gravity, which we all experience, actually satisfies time reversal symmetry. And to see that, what you imagine, for example, if you kick a soccer ball, it's going to go through a trajectory of a parabola and ended up somewhere else on Earth by gravity. Now, to see that this has time reversal symmetry, what you would need to do is to put the soccer ball at the end point, you reverse the direction of the velocity. And practically what you do is you just kick the soccer ball at the end point at that particular angle with a particular force. Now, if the velocity is exactly reverted, then the soccer ball is going to go through the same trajectory and ended up where you started. So this is an illustration of time reversal symmetry. In other words, what you see here is a symmetry between the forward motion and the backward motion of the particle. One thing that's very interesting about magnetic field is that it breaks time reversal symmetry. And so as an example, if I have an electron here coming into this region with a magnetic field perpendicular to the screen here, the electron is going to experience a Lorentz force. And as a result, because the Lorentz force is perpendicular to the velocity, it's going to turn around. Okay, so it forms a circular trajectory. Now, to test time reversal symmetry, what you would do is you start with the electron here at the end point, you revert the direction of the velocity. If the system has time reversal symmetry, then the electrons are supposed to trace back the trajectory as it comes in, as indicated by the dashed line here. But the law of physics would say that in fact the electron doesn't go back, and instead it further rotates following the trajectory as indicated here. This difference here is the time reversal symmetry breaking. So what we see is applying a magnetic field to an electron break the time reversal symmetry of the motion of electron. This ability of magnetic field to break time reversal symmetry has really very profound consequences in fundamental physics. There is a fascinating effect called the quantum Hall effect. In this effect, what we imagine is an electron moving in a plane, for example, let's say at the plane of the sheet here, and you apply a perpendicular magnetic field. Now, if you do that, if you inject an electron on the edge, it's going to go through the circular motion that I just described, hit the boundary, get reflected again, but again go through the same circular motion as my pointer is doing. And in doing so, it forms a one-way edge state at the edge of the sample of this two-dimensional electron gas. This one-way edge state is topologically robust. And as a simple illustration, you can put an obstacle in the pathway of the electron. Now, typically, if you imagine that if I throw a baseball at the obstacle, the baseball is going to bounce back at me. On the other hand, in the case of electron, in this particular system, it's going to figure out a way through the circular motion to go around the obstacle and just keep moving forward. So in doing so, what we see is that the system is topologically robust in the sense that it is robust against these kind of small disorder that you may throw on the trajectory of electrons. So the discovery of this kind of physical effect and the understanding of this effect in terms of the topological nature of the electron motion have led to at least 3 Nobel Prizes in the past 30 years, including the Nobel Prize in the past year, which really focus on the theoretical topological nature of the electron motion in these kind of systems. So I have reviewed the basic mechanism for controlling electrons. Now, let me also review how we control light. So when we think about controlling light, we tend to think about materials, and we think about the distribution of material in space. So here, one very important concept is the concept of refractive index. In general, when light or photon propagate in a material, the material are made out of atoms. And the presence of these atoms has the effect of slow down the propagation of light. The slowdown factor is what defined as the refractive index, which measures the ratio of the speed of light in vacuum to the speed of light in material. The higher the index, the lower the speed of light. A glass, many of you wear, for example, will have a refractive index of 1.5, which means that its speed is about approximately 50% lower compared with the speed of light in vacuum. As it turned out, when light hit the interface between 2 different materials with different refractive index, for example, between glass and air, they tend to reflect. And as a result, a glass tube like this can be used to actually guide light over long distance. And this is the fundamental aspect of the fiber optics that's a result of yet another Nobel Prize in Physics in 2009. Now, in early days of photonics, one tends to think about structures that are fairly sizable. For example, the core of a fiber is on the order of 50 to 100 micron. In these days, with the development of nanotechnology, there emerged a field called nanophotonics, where one tries to make very small structures with feature size on the order of maybe tens of nanometer, hundreds of nanometer, And in doing so, create fascinating property of light that I'm not going to go into great detail. And so this field of nanophotonics, unlike many of the things I mentioned here, has not resulted in a Nobel Prize yet. But we have a local hero here, our distinguished chair, Professor Noda, who made really fascinating structures and demonstrating really fantastic properties about these nanophotonic structures. So I have, up to this point, reviewed how we manipulate light and compare that to how we manipulate electrons. I think one of the interesting observations that you probably would have made is that, in fact, conceptually, we control these two fundamental particles in very different ways. When we control electron, we tend to just apply a field. But when we control light, that's not what we do, and instead we make a material distribution with a spatial distribution of refractive index. And this distinction is fundamental. Electron is a charged particle, so you can apply a field. Photon is a neutral particle. There's no naturally occurring field that interact directly with photons. Now, of course, there's in principle nothing wrong with these pictures. As you see, there are plenty of Nobel Prizes given on either side. However, one of the things that controlling electron can do very well is this issue of time reversal symmetry breaking. And I've shown you that if you want to break the motion of electron, the time reversal symmetry of the motion of electron, all you need is to apply a magnetic field. Same thing cannot be said about photon. It's actually very difficult to break time reversal symmetry. This may sound like a very profound concept, but in fact, it's your everyday experience. If I can see through a window, and if I can see you through a window, you should be able to see me through the same window. And in fact, that's our everyday experience. I can see Professor Noda sitting there, and I think he can see me as well. And that's really the fact that most optical structure and optical media, no matter how complicated it is, in fact satisfy this time reversal symmetry. They are fundamentally two-way medium. If I can see you, you can see me. Now, on the other hand, from a technological point of view, there is in fact a great demand in trying to break time reversal symmetry. For example, in information network, it would be great to have a device called an optical isolator. This is a device that allows light to go forward, but prevent any light to coming backward. And in doing so, it protects a particular device against the noise that may coming downstream. And this is very important because it fundamentally improves the robustness and the efficiency of the optical network, which in the end also translate into energy consumption of this network. Now, in order to be able to create this kind of medium or device, you would need to break time reversal symmetry because you would need something that's intrinsically one-way rather than two-way. People have been able to do so in bulk form with very large structures. They are macroscopic in size. But one of the fundamental challenges in photonics has been trying to do this at very small scale to make a very small device that you can also break time reversal symmetry. So our work is inspired by the pictures. This is probably the third time that I'm showing it, that the magnetic field can break time reversal symmetry for electron. So what we asked ourselves several years ago is, well, can we generate an effective magnetic field for a photon that breaks time reversal symmetry? Now, I emphasize the word effective because, as I mentioned, photon is a neutral particle. So by itself, it doesn't couple to any magnetic field. If you want one, you have to synthesize one yourself. Nature would not provide it for you, and that's where the word effective comes from. And the realization is that, well, in the vast majority of the structures that people have considered are what's called the static photonic structures. These are structures where the thing doesn't change. the refractive index distribution does not change as a function of time. On the other hand, you can get fascinating new physics, including the effective magnetic field, if instead you allow the material property of the refractive index to vary as a function of time. So I should briefly mention how in practice one can change the refractive index of a material. As I mentioned, refractive index is the slowdown factor. And so it measures how the presence of atoms slow down the propagation of light. Consequently, you should imagine that if you have more atoms, light will propagate slower. So imagine that you have a solid with a particular refractive index. Now you simply squeeze it. You just squeeze it like that. And in doing so, you increase the density. So in doing so, you should expect there are more atoms per unit volume, that the light will slow down more. And therefore, you should expect that the refractive index will go up as you apply a pressure. Now, therefore, if you apply a time-dependent pressure, you just squeeze, release, as you would expect for acoustic field, you would generate a time-dependent refractive index, and if you apply a sinusoidally varying pressure, you will basically get a time-dependent refractive index that looks like this. And our realization is in here, when you look at this very simple, a harmonic time-dependent variation of the index, the modulation phase here, in fact, is the effective magnetic field that coupled to photon. And to illustrate that, one need to go a step deeper in thinking about quantum mechanics. It is known in quantum mechanics that the electron actually doesn't directly couple to magnetic field, but couple to something called a vector gauge potential. And in simple terms, the effect of gauge potential is to introduce a direction-dependent phase. Imagine that you have electron propagate from spatial from point 1 to point 2. You will acquire two types of phases. One of them is a reciprocal phase that doesn't change its direction. The other one is the line integral of the gauge potential that changes sign as you flip the propagation direction. So in a nutshell, the gauge potential very clearly shows time reversal symmetry breaking, because forward and backward motion of electron in the presence of gauge potential are going to behave very differently. And what we recognize is that, in fact, the modulation phase here naturally create a direction-dependent phase for photon. Now, to do that, let me maybe give you a freshman introduction about some of the basic points about waves. So when we think about wave, and this is water wave, we tend to mathematically, you need to describe them in terms of a field. And for electromagnetic field, we think about, for example, electromagnetic wave or photon wave, we think about electric field. But mentally, all you need to think about is water wave, and the field is just a height distribution on the surface. Okay? So now we know that wave is a motion. So there are really two ways to think about the motion. One of them is just this picture, which is a snapshot of the wave field in time. So you look at a particular time, and you look at the field distribution, and you can see that it varies in space. On the other hand, you could also say, I'm going to be standing right on a point in here, just on a single point, and I record the wave amplitude as a function of time. In doing so, of course, I'm going to see the wave going up and down and up and down. So in other words, when we think about wave, we really are thinking about the variation of the field, for example, the distribution of the surface height, as a function of both space and time. And we can think about that in time by plotting the field as a function of time. There tend to be periodic that define a period, and then we define a frequency which is reciprocal to the period that measures how fast the wave varies in time. Alternatively, we can plot the field as a function in space for a given time. The field will tend to be periodic in space. We will have a spatial periodicity, and we will have a wave vector that measures how far the wave varies in space. So the entire physics of the wave is encapsulated in the frequency and the wave vector. By the way, frequency for light means color. So when you see different color, you are seeing different frequencies. We tend not to think about wave vector when we think about light. On the other hand, if you look at the water surface, the water wave is very apparent what a wave vector is. It's just the distance going from one maximum to the other. Now, the essence of the wave physics is in fact the realization that the spatial variation of the field and the temporal variation of the fields are related to each other. So this is encapsulated, for example, in any wave equation, including the simplest one, the Helmholtz wave equation, basically says that the frequency, which is the temporal variation, and the wave vector, which is the spatial variation of the field, are actually linearly proportional to each other. In other words, the faster the field varies in space, the faster the field varies in time. And so it's really the space-time connection that's encapsulated in the wave physics. So now what I would do is to try to illustrate how the gauge potential shows up in a waveguide. So let me tell you something simple about the waveguide. So in a waveguide, when we, as I mentioned, you will have light bouncing back and forth at these interface. So the wave is going to be confined, for example, in the silicon region. And if you look at the field distribution of the electric field, you can have different spatial distribution. For example, I'm plotting here, the red and blue here correspond to large positive and negative field. So you have a field that's an even mode, and you have a field that's odd mode. Now, as I mentioned, you can see that this one has a stronger variation of the field distribution in space, and so they have higher frequency, and this one has lower frequency. When you think about a static structure, the frequency of light does not change. And when light is passing through, for example, your glass, the color of light does not change. On the other hand, if you now modulate the structure, for example, if you vary the refractive index in this gray region in a harmonic way, then you can couple light at different colors together. Now, in this case, if at time equal to 0, you start with the even mode, and you look at the amplitude or the probability that the photon have different color, is going to oscillate as a function of time. And that's simply an indication that you can couple light with different frequency together with a dynamic modulation. One of the very important points when you look at it is that the probability variation as a function of time actually is independent of the modulation phase that you put in. And if you read a modern physics textbook, this is the classic definition of a gauge potential. It is a variable that by itself doesn't influence the intensity dynamics. And you can go a step further. You can write down, somebody talk about the matrix formalism of quantum mechanics. You can write down the matrix of the system. And what you will see is that the upward transition in frequency and the downward transition in frequency actually acquires opposite phase. And therefore, what you have here is a direction-dependent phase in frequency space. You can convert that into a direction-dependent phase in real space. So what you would do is you imagine you have two of these two-level systems. When a photon is coming from the left, it will go through an upward frequency conversion on the left, propagate, goes through a downward frequency conversion on the right, and goes out. And it will acquire a phase that looks like this. On the other hand, for a photon that's coming from the right, it will go through an upward conversion on the right side and a downward conversion on the left side. And in doing so, acquire a phase that is different for precisely the sign difference between the upward and downward transition. In doing so, therefore, you get a direction-dependent phase. And with an interferometer, you can then convert this into an intensity response that's non-reciprocal. So here is the initial numerical calculation. What we do is we modulate the refractive index in these two shaded regions at the same frequency, but with a modulation phase that differ by pi over 2. In doing so, an even mode that's coming in get converted to an odd mode. But if you send the odd mode back, it doesn't go back to the even mode, but instead remain in the odd mode. And that's a clear indication of time reversal symmetry breaking. And this is already sufficient to give you complete optical isolation. And this theoretical concept has received fairly substantial experimental confirmation. Here is one of the experiments we carried out in collaboration with Professor Eggleton in Sydney. And he constructed an interferometer that looked like this. One arm of the interferometer has two acoustic optic modulators. Each of them are modulated with the same frequency, but with a different modulation phase. He then measured the transmission of light from left to right and from right to left. And he plotted the transmission in both directions as a function of the phase difference between these two modulation phases. What you see, like any interferometer, is that the transmission varies sinusoidally as a function of phase difference. However, the left to right transmission and the right to left transmission are completely different. And in fact, even in a relatively simple setup, you can get a contrast where the right to left and left to right differ by more than 10-fold, in spite of the fact that you are using acoustic optic modulation, which has very low frequency compared with the frequency of light. This idea has also been demonstrated in a collaboration with Professor Michal Lipson's group at Columbia, where one used nanophotonic technique to demonstrate this effect on a silicon chip with electro-optic modulation. So I've shown you how we can get a effective gauge potential for light. The natural step next is then to convert this into a effective magnetic field so that you can do many of the fascinating physics of electron and magnetic field, but now with photon. So for example, in electron, if you have a tight binding lattice, which are just electrons hopping around sites, if you apply a magnetic field, the effect of it shows up in terms of a phase as electron goes around the edge of one of the unit cell. So to implement that in the photonic side, what you would do is you imagine a lattice of resonators that look like this, where the nearest neighbor site has different resonant frequency. You will modulate the coupling constant between the nearest neighbor site with a frequency equal to the frequency difference, but with a modulation phase. This modulation phase distribution then gives you the effective magnetic field. For example, if you have a uniform effective magnetic field, you have a zero effective uniform modulation phase, you have a zero effective magnetic field. On the other hand, if you have a linear variation of the modulation phase in space, you have a uniform magnetic field. So in doing so, you can do a Lorentz force, as we have mentioned in the very beginning, but for photon. So you imagine two regions with different modulation phase distribution. On one side, you have zero magnetic field, so the photon will just propagate straight. On the other side, you have a non-zero magnetic field, so when the photon comes in, it's going to bend. And that's basically what Lorentz force would tell you. And you can also do this one-way edge state by taking a resonator lattice, applying a perpendicular effective magnetic field with the modulation phase distribution. This gives you a one-way edge mode that is dynamically induced. So if you put a source here, you can see the electromagnetic energy actually just goes straight up, but nothing comes down. And that's the one-wayness of the wave propagation. And this thing naturally goes around a defect that you put at the edge of the sample without any back reflection. So you can create these kind of topologically robust propagation inside these kind of dynamically modulated photonic structure. In the last part of the talk, I would like to show some of our recent work where we generalize this concept of a synthetic effective magnetic field from the real space into what we call the synthetic dimension. And to illustrate what the basic consideration is, So the basic motivation here is to try to explore higher dimensional physics in lower dimensional physical structures. We all know, of course, that we live in a three-dimensional world in space, or if you add the time dimension, then we live in a 3+1 space-time dimension. On the other hand, there's tremendous amount of richness in thinking about the physics, not constrained by the three-dimensional world that we live in. So in that sense, it would be very interesting to figure out a way so that you could actually eventually experimentally explore the physics that occur in higher dimension in the system that we have available in the lab, which is fundamentally 3+1 dimension. So that's the motivation. So now you ask, how do you go about doing it? This is, in fact, if you think about it, a very simple idea. All you need to do is, well, go invent a dimension and add to the physical system. So I'll try to illustrate this with a simple example. Suppose, as an artist, you are tasked with describing a three-dimensional object. These are basically cylinders with varying height. But you are constrained with only a two-dimensional canvas. So you are trying to describe the three-dimensional world in a two-dimensional field, in a two-dimensional space, which is not an uncommon task if you think about painting. So a natural idea that you would do, if that was your task, of course, is that you would try to represent the height of the cylinder with different colors. So a short one being blue and the long one being red, and so on. So you could actually represent three-dimensional physics with a two-dimensional representation in space, but you add one extra dimension, and in this case, the extra dimension is the color. Or as I mentioned throughout the talk, color is frequency. So you add a frequency dimension, in this case is your synthetic dimension. This actually is a very useful concept in thinking about trying to synthesize higher dimensional physics in lower dimensional physical system. So let me give a construction of what I would be using, and that's what's called a ring resonator. This is just take a waveguide, for example, a fiber, and just wrap around and connect the end together, so it forms a ring. Now, in this system, if you imagine a wave that's traveling around the circumference of the ring, as it goes around the ring once, it has to come back to itself. So consequently, the field distribution along the ring cannot be arbitrary, but has to satisfy a periodic boundary condition in the sense that if you go from x equal to 0 to x equal to L, L being the circumference, the field value has to be the same. And so consequently, you can only have a discrete set of field distribution that can be supported by the ring. And as mentioned, every spatial distribution translates into a particular frequency. So having these different spatial distributions translate into having each of these modes having different frequency. So out of a single physical ring here, which is a zero-dimensional object, you now have a one-dimensional array of different frequencies that you can think of. And so in a zero-dimensional thing, you can think about a one-dimensional world. Now, of course, if this is a stationary ring that doesn't vary as a function of time, it's not terribly interesting. All these frequencies just does not mix, they don't couple to each other. But we already show you how you mix them, and that's just by putting a modulator in there. And as you do that, you can choose the modulation frequency to be equal to the frequency spacing between all these modes. And in doing so, you couple all these modes together. And so a ring here, therefore, forms what's called a one-dimensional tie binding model. But essentially, it's just the photon hops along the frequency axis. So you actually get a synthetic one dimension out of the zero-dimensional world. Now, in this case, the modulation phase here shows up basically along as a hopping phase along the direction along the frequency axis. So with this, now you can take a one-dimensional object, a one-dimensional array of rings, and simulate a two-dimensional world. And in this case, each of the object will have an additional dimension coming from the frequency. So the physics of this is actually described by a two-dimensional space with a frequency axis and the real axis. The modulation phase here, if you choose them to be linearly chirped like this, give you an effective magnetic field that is uniform, perpendicular to the synthetic space. And therefore, you get a one-dimensional edge mode, just like one-way edge mode, just like what we're saying, that in the synthetic space is going to go around the edge of the synthetic space. This look in this picture like what we have talked about in real space. But in physical picture is very different, because what you really have is that you have lots of frequencies or lots of color of light for the ring at the edge of the sample. And as the time evolves, all these frequencies get collapsed into a single frequency in the middle of the array, and then they re-expand again, and then they get collapsed again. So you actually see a very interesting possibility of manipulating the spectrum or the color of light with this kind of dynamic modulation concept. Now, in the last couple of minutes, let me very briefly also show a slightly fancier example. Lately, there have been very interesting things that people talk about, something called a wild Hamiltonian in 3 dimensions. And this is a magnetic monopole in momentum space that have very interesting topological effect. And people have explored them in very complicated 3-dimensional structure, both in electron world as well as in the photonic world. Now, what we show here, without going into detail, is that instead of doing a very complicated 3-dimensional structure that's difficult to make, you can take a 2-dimensional structure that's straightforwardly makeable by modern lithographic technique, and then you put modulator, for example, a 2-dimensional array of rings, and you put modulator on each of the rings. You control the modulation phase. You could actually do wild point physics, which is inherently a 3-dimensional topological physics, but now in a 2-dimensional system with added frequency dimension. So with that, let me summarize. So what I hope to convey are really some of the excitement in thinking about dynamic photonic structures, in thinking about structures where the refractive index vary as a function of time. And what we argue is that combining the structure aspect, the spatial distribution of the refractive index, with the temporal modulation of it, actually give rise to a very rich set of fundamental physics effects that point to the combination of topological physics with photonics. In addition to the fundamental interest, this also indicates new capabilities for the control of light for information technology. So with that, let me acknowledge many of my former students and postdocs who have contributed to this work. In particular, 2 of my early students are both professors at leading research universities in the United States and are building up their own strong group in this area, Professor Zhongfu Yu and Professor Ke Jiefang, as well as my current students and postdocs who are working on this. And I should also acknowledge my experimental collaborator, Professor Michal Lipson in Columbia and Professor Ben Eggleton in the University of Sydney. So with that, let me stop and thank you for your attention.